Example problems. Example 1, water potential equation. What natural phenomenon is similar to the plunger pulling up on the column of pure water in scenario D? Example D illustrates transpiration, or water moving from the roots to the leaves in a tree. Compare the potentials in the two pictures. The lower potential is in the leaves and the left side of the U-tube. So overall, we have a lower potential on this left side when we have this negative pressure or tension here. Example 2, water potential equation. A potato cell with a solute potential equal to minus 1.5 megapascal is placed in an open beaker containing a solution with a solute potential equal to minus 1.2 megapascal. The pressure that the cell wall exerts is 0.3 megapascal. Assume that the volume of the beaker is much larger than the volume of the cell, and equilibrium is reached when the cell's water potential matches the beaker's water potential. The beaker's water potential cannot be changed significantly by diffusion of water to or from a single cell. All right, so there's two parts here. A, has the system reached equilibrium, and how do you know? And B, what is the net direction of osmosis? So I want to label what's going on here. So first of all, the solute potential of the cell is minus 1.5 megapascals. I'm going to leave units off here just for simplicity, but we'll see them on the next slide. The beaker is open and has a solute potential of minus 1.2 megapascals. Now, if all we cared about was the solution potential based on the amount of dissolved solute, we could look at this and say there's greater solute potential on one side than the other, so this is the direction that the water will flow. But we've talked in previous questions about how we can't just look at the amount of dissolved solute to determine the direction of the water flow. We also have to look at the pressure potential. How much pressure is the cell wall exerting? And it's the combination of those two things that helps us to determine the overall water potential. So we're being told that the cell wall, given by these blue arrows pushing outward, is exerting a pressure equal to 0.3 megapascals. So let's use that information to determine if the system has reached equilibrium and what the net direction of osmosis is. So in order to know if the system has reached equilibrium, we need to know what is the water potential inside the cell and what is the water potential of the surrounding water. So inside the cell, we have the pressure potential of the cell, or the pressure exerted by the cell wall, which was given as 0.3 megapascals, plus the solute potential inside the cell, which was given as minus 1.5 megapascals. So you have an overall potential of minus 1.2 megapascals. Now, the potential of the surrounding water is the pressure potential of that water, which is 0 because it's an open container. There's no pressure exerted on the water itself. We don't have any plunger or anything like that. Plus the solute potential of the water, which is given as minus 1.2 megapascals. So these two water potentials inside and outside the cell are equal, and that means that the system is in equilibrium. So what is the net direction of osmosis? Well, the net flow of water, or osmosis, is always from higher to lower water potential. Water flowed into the potato cell. Equilibrium was reached when the potato cell's cell wall exerted positive pressure of 0.3 megapascals, pushing water against its gradient. Example 3, water potential equation. How was equilibrium reached when a plant cell was placed in a beaker of distilled water as shown in the diagram? So we started with distilled water, where the pressure potential and solute potential were 0, overall water potential was 0. Immediately after being put into this distilled water, pressure potential was 0, solute potential was -2. We had an overall potential of -2. After being in distilled water for some time, we now have a pressure potential of +2. Our solute potential is still -2. We haven't added or removed any solute. Now we have an overall potential of 0. So let's talk about how this happens. So immediately after the plant cell was put into the water, we have a negative potential. So water will flow from higher to lower water potential into the cell, okay? Because outside the cell is just distilled water with a potential of 0. Inside the cell is a negative potential. So water will flow from higher to lower water potential into the cell. When the water flows into the cell, the pressure potential in the cell increases. So the cell wall is exerting pressure until enough positive pressure, right? Until we get to the same positive pressure potential of plus 0.2 megapascals, that the cell's water potential equaled the beaker's water potential. Okay, so once they both have a water potential of 0, then equilibrium is reached. And that happens when water flows into the cell, and as it does, the pressure potential inside the cell provided by the cell wall increases till we get to that 0. Example 4, water potential equation. Elodea is a common freshwater weed. Why don't Elodea cells in a beaker of water burst even though their cells are packed with solutes? B, what is the water potential of the water in the beaker? And C, what is the water potential of the Elodea cells? All right, so in part A, the reason that the cells don't burst is because plants have cell walls, right? So the cell walls of the Elodea resist osmosis and they add a pressure potential. What is the water potential of the water in the beaker? The beaker is an open container, so the water potential of the water in an open beaker is 0 megapascals. And C, what is the water potential of the Elodea cells? The system is at equilibrium, so the water potential of the Elodea is also 0 megapascals. The Elodea cell's pressure potential and solute potential are equal in magnitude but opposite in sign, adding up to 0 megapascals. Example 5, water potential equation. A plant cell has a solute potential of -7 bars and a water potential of 0 bars. It is immersed in distilled water. What is the cell's pressure potential at equilibrium? So just a couple things. There's a lot of vocabulary here that can make this really hard, but we are told that psi S is -7 and the water potential, which is psi, is 0. Okay, so let's look at the next slide and use the equation to do some calculation to figure out the cell's pressure potential at equilibrium. So we know that for distilled water, the water potential in the beaker is 0 bars. At equilibrium, the water potential of the plant cell then, psi for the cell, the overall water potential for the plant cell must be equal to that of the water, or 0 bars. Okay, so the water potential for the cell we know is the sum of the pressure potential and the solute potential. And we know that at equilibrium, this has to be the same as the overall water potential for the beaker, and that's 0. So I solved for the pressure potential of the cell and substituted the water potential for the cell, which is 0, and the solute potential for the cell, which we were told is -7, and I get a pressure potential for the cell equal to 7 bars. So what this means is that in order for equilibrium to be established, water will flow into the cell, And as it does so, the cell wall will provide an external pressure. And water will continue to flow until the pressure provided by the cell wall is 7 bars. Example 6, water potential equation. A plant cell has a solute potential of -7 bars and a water potential of 0 bars. It is immersed in a beaker containing a solution where the water potential is equal to -4 bars. What is the cell's water potential and pressure potential at equilibrium? So we know that the water potential of the water in the beaker is -4 bars. At equilibrium, the water potential of the plant cell must equal the water potential of the beaker, or -4 bars. So my water potential equation is the overall water potential is the pressure potential provided by the cell walls plus the solute potential of the cell. So if I put a -4 in here for my overall water potential for the cell at equilibrium, as we established, then the pressure potential provided by the cell wall plus the solute potential inside the cell, which we're told is -7 bars. And we can solve from there. So the pressure potential then is -4 minus -7, or 3 bars. So to answer the question, the cell's water potential at equilibrium is -4 bars, and the pressure potential at equilibrium is 3 bars. Example 7, solute potential equation. What is the solute potential of a 2 molar sucrose solution in an open beaker at 25 degrees Celsius? In order to solve this, we can just use the solute potential equation provided. We just have to make sure that our temperature is in Kelvin. So if we have 25 degrees Celsius, we need to just add 273 to that. So we get 298. And given the units for R that we're using, our final units of pressure will be in bars. So I is always 1, right? And we're talking about sucrose here. We're assuming that it's 1. The concentration is 2 molar. Let's see. R is 0.0831 liter bar per mole Kelvin. And then temperature in Kelvin is 25 plus 273, or 298. And just in a calculator, we get -49.5 bars. And I just want to make sure we see units here. Molarity is moles per liter, which means that if I multiply that by liters per mole, that cancels. And then Kelvin on the bottom of this fraction, and the top here cancels, and we're left with units of bars. Okay, so -49.5 bars. Example 8, solute potential equation. A cell wall with a water potential of 15 bars is placed in a 2 molar sucrose solution in an open beaker at 25 degrees Celsius. What will its final water potential be? And B, can we calculate the cell's solute potential or pressure potential at equilibrium? Okay, so in part A, we're asked, what will its final water potential be? So first, we're given enough, so remember, first of all, overall water potential is pressure potential plus solute potential, okay? So the first thing we can do is calculate the solution's solute potential, okay? Because we're given the concentration, we're given the temperature, and we're told it's sucrose. So I is 1, concentration is 2, R is a constant, and then the temperature is 298. We actually did this calculation back in example 7, if you want to look back. But we get a solute potential of -49.5 bars. Now, next part is, what is the final water potential? So we can calculate the water potential, recognizing that the pressure potential of water in an open container is always 0 megapascals. So we're told that this is an open beaker. So the pressure potential is always 0. And that means that the overall water potential, the cell's final water potential, will match the solution's water potential, minus 49.5 bars. Now, can we calculate the cell's solute potential or pressure potential at equilibrium? We can, we just have to make an assumption. In this situation, if we can infer that when placed in a sucrose solution with such a high solute concentration, 2 molar, the cell will become flaccid as all its liquid leaves. Okay, so if you put the cell in a really highly concentrated sugar water, then water will rush out and it will become flaccid. And at that point, the cell walls cannot provide any pressure anymore. So the pressure potential will be 0 bars. So I can solve again using the same equation, but with a pressure potential equal to 0 bars. And then the cell's solute potential is minus 49.5 bars. Example 9, solute potential equation. A cell has a pressure potential of 3 bars and a solute potential of minus 5 bars. The cell is then dropped into an open beaker containing 0.1 molar sucrose at 27 degrees Celsius. Will the net flow of water be into the cell or out of the cell? So let's start by calculating what the solute potential of the water in the beaker is before we put a cell in it. So using our solute potential equation, I is 1, the concentration of the sucrose is 0.1, R is our constant, and we're told that the temperature of that solution is 27 degrees Celsius, so plus 273 gives us temperature in Kelvin. So the solute potential, and this is the beaker, right, is minus 2.5 bars. The water potential, the overall water potential of the beaker solution is also minus 2.5 bars because we have an open beaker, so the pressure potential is 0. Now let's compare this overall water potential with that of the cell that's dropped into the beaker. So here's the water potential of the cell. It's the pressure potential, which is given as 3 bars, plus the solute potential, which is given as minus 5 bars. So we get an overall water potential of the cell equal to minus 2 bars. So if this is my beaker, this is my cell. Outside the cell, I have a water potential of minus 2.5, and inside I have a potential minus 2.0. The net flow of water will be out of the cell into the beaker until its water potential is equal to minus 2.5 bars and equilibrium is established.